Hello everyone, I'm Bongjoon from KAIST. Today I'm going to talk about NeuMMU, architecture support for efficient address translation in neural processing units. This work is done by my colleague Youngeun Kwon, Yujeong Choi, and Professor John Kim and Professor Minsoo Liu. Let me first explain the motivation of our work. There have been numerous academic and industrial work proposing various forms of machine learning accelerators, also known as neural processing units, which helps accelerate a broad range of neural network-based algorithms. Given the large number of NPU architecture proposed in past literature, it is a bit challenging to define a generic NPU architecture design. However, a common characteristic that we observe from the majority of these architecture design is as follows. First, many of these NPU architecture employs a spatial grid of processing elements. Second, the memory hierarchy consists of a large on-chip scratchpad memory which is populated by DMA units. So an interesting question is, why does NPU utilize a scratchpad memory and a DMA, rather than, say, using a cache? To understand the reason behind such a design decision, let's take a look at how the software stack looks like for NPUs. When a deep learning framework is given a target application to accelerate, it first analyzes and generates a high-level graph. Then the low-level IR, the software layer conducts some optimization and finally generate machine code that is ready to be executed on NPUs. Now, from a memory management perspective, the runtime software is able to precisely estimate the overall memory usage and check whether it fits within the physical capacity of NPU memory. NPU maps the data structure directly into the physically addressing mode, rather than using page-based virtual memory. As shown in this slide, for instance, the key input data structure, the input activation, and weights are allocated with the large segments within the physical address space, and the NPU utilizes the base and bound address to index its physical memory. So coming back to the question, why do NPUs primarily use a scratchpad memory and a DMA? Notice that conventional deep learning applications utilizing convolutional or fully connected layers exhibit highly deterministic memory access patterns. The underlying NPU microarchitecture is specifically designed to utilize such deterministic data flow of DNN applications. Processing elements access data in a highly regular and deterministic pattern, and when it comes to populating the scratchpad memory, the DMA unit moves data between the on-chip and off-chip memory in a highly regular and deterministic fashion. So far, this method worked all fine. However, emerging deep learning applications utilizing embedding layers, for instance, speech recognition, machine translation, and recommendation exhibit highly irregular data flow, limiting the types of workload that can be accelerated by these NPUs. Okay, so let me explain how embeddings are utilized in modern recommendation model. The goal of the recommendation model is to predict a preference score between a user and an item. In this example, there is a user Bongjoon, which is me, and we need to recommend a movie among these three. The model already has the embedding table which contains embeddings of every movie, and this user also has personalized embedding vector. First, among the large embedding table, the model gathers the corresponding embeddings of these three movies. Then pass the user and movie embeddings to DNN layers. And through DNN computation, we can predict the preference score between the user and movies. If you think about the number of users serviced by big tech companies like Facebook or YouTube and the number of films created in human history, you will know the size of embedding tables are huge. Indeed, the size exceeds hundreds to thousands of gigabytes of memory footprint. But NPUs only have several tens of gigabytes of DRAM, causing a problem, which is where to put these embedding tables. To overcome the memory capacity challenges of embedding layers, an existing GPU-based solution employs model parallelism to partition the embedding tables across multiple GPUs. As illustrated in this slide, let's assume a system with 4 GPUs connected through a GPU-side interconnect as shown in green-colored arrows. As embedding tables for recommendation are in the order of several hundreds of gigabytes, the bandwidth-optimized GPU memory, which is only in the order of several tens of gigabytes, cannot hold entire embedding tables. As such, a GPU system employing model parallelism partitions the embedding table into 4 pieces and distributes them across 4 GPUs. For instance, consider a scenario where GPU 2 gathers 2 embedding vectors allocated in GPU 0 and GPU 2. Now, as today's GPU has a properly functioning MMU with a unified virtual memory, GPUs can use NeuMMU to access any given data allocated in any given remote GPUs. Now, imagine what would happen if we were to use MPUs instead of GPUs. Since the MPU has no way of knowing where the data is located when it is outside its local memory, the CPU must intervene in the entire process when loading data from remote memory. Specifically, the CPU must first copy the embedding vector from MPU 0 into the CPU host memory. Then the CPU must again copy this embedding vector to the requesting MPU 2. All this process adds significant latency overhead, resulting in significant performance loss. Here, we show the results of breaking down inference latency into 4 categories: gem, reduction, else, and embedding lookup. Notice that the latency to gather the embedding vectors, colored in yellow, accounts for a much larger fraction of execution time than the DNA execution itself, which is shown in black. So, as shown through these examples, we can see the importance of having a functional MMU in widening the range of applications the MMU is able to accelerate, motivating the design of MMU for MPUs. So you might ask, why not use IO MMUs for handling the address translations as is? Let's switch gears and talk about what are the key challenges of utilizing IO MMUs for the MPU. Before we discuss key challenges of IO MMUs, let me first summarize some of our evaluation methodology. We chose 6 representative neural network topologies that cover 3 CNNs and 3 RNNs using a batch size of 1 to 8. When modeling performance, we developed an in-house cycle-level simulator that models a Google TPU-like systolic array microarchitecture, which we cross-validate against Google Cloud TPU. Now, if an MPU MMU were to be introduced to this picture, a virtual to physical address translation of input activation and weight tensors must proceed to allow the DMA unit to determine where within the physical address space the tiles are located. So, the important research question we seek to answer in our work is, how big is address translation overhead, and what architecture supports are needed to alleviate the address translation overheads? To understand the performance limiting factors of address translation in MPUs, let's first understand the nature of DMA tile fetches in MPU architectures. The input activation and weight tensors are structured 4-dimensional shape. As mentioned before, these 4-dimensional tensors are also blocked and partitioned into 4-dimensional tiles to be fetched into the on-chip scratchpad memory. But notice that these 4-dimensional tensors are only logical representation. As shown in this slide, how these tensor tiles are mapped to physical DRAM is single-dimensional. Multiple single-dimensional contiguous segments are sparsely scattered across the physical address space. Now, because these contiguous single-dimensional segments are sliced and translated in page boundary, the DMA unit ends up generating multiple address translation requests per each tile fetches. In our work, we refer to such divergence of page translation requests as page divergence. An interesting research question is, how bad is it? Here we show the number of distinct page accessed per each tile fetch for the 3 CNNs and 3 RNNs. As shown, a single tile fetch amounts to several hundreds of distinct page translation on average, reaching up to 1,000 in worst-case behavior. What is more concerning is that these hundreds to thousands of page translation requests are generated in bursts, rather than interspersed across large periods. In this chart, we show the number of translation requested within a 1,000 clock cycle time window. As depicted, the NPU MMU generates large spikes of address translation requests within a short time frame. Now that we discuss distinct characteristics of DNN address translations in NPUs, let's talk about how effective conventional IO MMUs are in dealing with such bursty address translation requests. What's shown here is a high-level system overview of a host CPU interconnected with various I/O devices such as GPUs, DSPs, and MPUs. To facilitate the address translations of I/O devices, modern systems contain a unit called IO MMU, which the I/O devices can request address translations on its behalf. Inside the IO MMU, there are 8 to 16 number of hardware page table walkers and an IO TLB. These hardware page table walkers are baristas at a Starbucks ready to service customers asking for a cup of coffee if we think customers as address translation requests. When utilizing IO MMUs for GPU address translations, the amount of address translation throughput available at the IO MMU is typically sufficient enough to properly handle them. This is because GPUs have address coalescing units within each GPU core that filters down the address translation request bandwidth, and a multi-level GPU TLB hierarchy that allows GPUs to effectively capture the locality within address translation requests. When it comes to MPUs, however, the raw volume of address translation requests arriving at the IO MMU simply overwhelm the limited address translation throughput available within the IO MMU and its IO TLB. This is the performance results of using IO MMU as is in the NPU case. As shown here, the performance loss is huge if we use IO MMU as is, incurring 95% performance overhead compared to an oracular MMU. So far, we discussed the challenges of utilizing a vanilla IO MMU as is for NPUs, motivating an MMU architecture tailored for DNNs. Let us move on to discuss our proposed NeuMMU design, which is optimized for translation throughput first rather than for translation locality as done in GPUs or CPUs. One of the first key observations we make is that the burst of translation requests sent to the IO MMU are actually far under the same virtual page, but the IO MMU still independently walk the page table because they miss at the IO TLB even before the first missed translation is finalized. So our design is a microarchitecture called PRMB, short for Pending Request Merging Buffer, which is designed to remove such redundant page table walks. The role of PRMB is better illustrated with the example shown in this slide. The 3 TLB missed translation on the left fall under the same virtual page. However, the MMU doesn't have PRMB, so it has no idea that the 3 translations are requesting the same virtual page. It allocates 3 different page table walkers, and each assigned page table walker starts redundant page table walks for the same virtual to physical translation, which waste valuable address translation bandwidth. The benefits of our proposed PRMB microarchitecture is that the MMU tracks which page table walkers are currently handling which virtual to physical translation, so it knows that the 3 TLB missed translations fall under the same virtual page, so it assigns a single page table walker, generating a single page table walk rather than initiating 3 page table walks, amplifying the effective translation throughput by 3x. Here are the performance improvements offered by adding PRMB microarchitecture. For the 3 CNNs, PRMB helps remove significant fraction of redundant page table walks, enhancing overall performance. However, the performance improvement to RNNs are not as high as CNNs, since RNNs have fewer redundant page table walks that can be removed by PRMB. Our second proposal is to increase the number of page table walkers to properly accommodate the burst of address translations in NPUs. This chart shows the performance improvement of adding additional page table walkers on top of our first optimization, the PRMB. Adding additional page table walkers dramatically closes the performance gap between NeuMMU and the oracular IO MMU. So with the aforementioned two optimization, we reached performance close to an oracular MMU. An interesting question, however, is why should we even bother adding PRMBs? Why not just add a large number of page table walkers to match the translation throughput requirement of MPUs? To answer this question, consider the graph in this slide, which shows normalized performance on the left axis and normalized energy consumption on the right axis. The far right design point has 4,000 page table walkers with no PRMB, meaning our MMU has sufficient amount of translation throughput, but there is no means to filter out redundant page table walks. As we move from right to left, we are reducing the number of page table walkers while adding more PRMB entries per each page table walker, hoping that the translation merging effect of PRMB boosts effective translation bandwidth by reducing redundant page table walk. As shown, overall performance stays competitive until reaching the middle design point of this graph, while energy consumption monotonically decreases. Such result highlights the importance of properly filtering out redundant page table walk using our PRMB microarchitecture, as more page table walks mean more energy consumptions. Our final proposed optimization is the translation path register, which caches the most recent page table walk information but designed in a highly cost-effective manner by utilizing the unique application characteristics of DNNs. In this slide, the upper left table shows the bin-level representation of TLB mistranslation, assuming a 4-level hierarchical page table walks. Therefore, the TLB mistranslation has L4, L3, L2, and L1 indices, which are the offset of each level of page table. When the TLB mistranslation arrives at our NeuMMU, it first looks up the translation path register before walking the page tables and check whether its L4, L3, or L2 indices match with the translation path register. Since the translation path register is not warmed up yet, in this example, the indices doesn't match initially. Then the TLB mistranslation is assigned to a page table walker, and the page table walker walks the page table 4 times since we assume 4-level page table walks. When all of the page table walks finishes, its result for L4, L3, L2 page table walks are cached in the translation path register, similar to how conventional MMU caches work. Then, when a second TLB mistranslations, whose L4, L3, and L2 indices are the same as the first TLB mistranslation, arrives and asks for a translation. It looks up the translation path register, and this time the indices matches. Therefore, skipping the first 3 page table walks, needing to walk only the last level of page table walk instead of 4. Since the performance is already close to that of an oracular MMU after adding massively parallel page table walkers on top of PRMB, this slide primarily focuses on the hit rate of the translation path register to quantify how effective our proposal is in reducing the number of page table walks. As shown, the hit rate of L4 and L3 indices are over 99%, even there is only 1 register per each level, which shows the cost effectiveness of the translation path register. You might wonder why the translation path register is so effective even with a single pair of registers. To understand reason behind this, let me explain about our key observation, which is any given DNN layer typically utilizes a handful of key data structures such as input-output activations and weights, all of which are mapped contiguously in the virtual address space. And because DNNs exhibit streaming behavior, each tile fetch is close to each other on virtual address space, making them very likely to share common L4, L3 indices. As a result, high hit rate for the translation path register. Overall, our proposed new MMU architecture reaches 99% of the performance of an oracular IO MMU, while significantly reducing the number of page table walks by 19x, which helps improve energy efficiency as well. So far, we have focused on enabling address translation in MPUs with our new MMU architecture design. With our new MMU in place, we are now able to properly support NUMA capability in model parallel deployment of memory capacity limited recommender systems, as we have outlined in the early part of this presentation. Coming back to our multi-MPU system example, with the help of our new MMU design, MPUs are now able to directly read embedding vectors from remote NUMA zones in a P2P fashion, without having to make intermediate copies at the CPU host memory. If you look at the yellow fraction, which is time taken to gather embeddings, you will know that without direct NUMA access capabilities, the latency to gather embeddings take up significant portion of execution time. With our proposed new MMU in place, the latency to gather embeddings from remote NUMA zone is significantly reduced, improving overall performance. So here are the three key takeaways from our work. Our work is the first work to explore architecture support for MPU MMUs that enable address translations. Our work conducts a data-driven analysis on the address translation properties of conventional and emerging ML layers. NeuMMU is a throughput-centric MMU design that provides 99% of the performance of an oracular IO MMU. Thank you for watching our video. I'll be happy to answer your questions if you send them through email bongjoon.hyun@gmail.com.